Chapter 20 deals with electromagnetic induction. So in previous chapters, we've seen where we have an independent voltage source, right? Maybe it's a set of parallel plates that are charged, or if it's a battery or something like that. That's our energy source, our power source that drives a current through a circuit and powers these components. There's another way that we can generate voltage and current, and that's through magnets. So we can use moving magnets to generate a voltage and a current. So we saw in chapter 19, what's the relationship so far? A moving charge in a constant magnetic field will experience a force due to the right-hand rule. So if a charge is moving, it's going to accelerate in a certain direction if it's in a uniform magnetic field. Then we've got a current carrying wire also experiences a force, right? The wire will bend if it's in a magnetic field. So moving charges will experience a force due to a magnetic field. Then we have a current carrying wire generates its own magnetic field. So we see that there's a magnetic field that surrounds a current carrying wire. So that's our relationship so far between moving charges and magnetic fields. So Michael Faraday's experiment, so the legend has it is his experiments, he accidentally discovered this while he was teaching a class. So what he did was he had a coil, he had a loop of wire that was connected to a current needle. So it told him what direction the current was passing through the coil, and he brought a magnet close to the coil, and he saw that the needle deflected. Right, so he took the north end of a magnet and he put it into a coil, and he saw the needle deflect momentarily, just for a short amount of time. Then it came back to zero. When he pulled the magnet back out, it deflected in the other direction. And experiment 9, we're going to use a simulator where we do the same thing. Right, we take the north end of a magnet, put it into a coil. We're going to see a bulb light up. Pull it out. We're going to flip the magnet, put the south pole of the magnet in. We'll see the bulb light up. So this was his discovery, that if he pushed a magnet into a coil, or if he pulled it out, there was a temporary current. Right, there was a temporary current passing through the circuit. So if we take another coil that's connected to a battery and a switch, if we close this switch, we see that there's going to be a current I, going from the positive end, going around this coil, and then back to the negative end. This loop will cause a temporary deflection in this needle. Again, just like the magnet. And then when you open the switch, the current will change direction momentarily. After a little bit of time passes, the current needle will go back to zero. So a coil with current passing through it acts as a bar magnet, which kind of makes sense from chapter 19. If you remember our right-hand rule for a current carrying wire, there's a magnetic field that's traveling in a circular path around that current carrying wire. And a loop, or a coil, is just a series of current carrying wires. So this diagram right here is a single loop. If I want to find out where the north end, right, the north pole of this bar magnet is pointing, I'm going to use another right-hand rule here, and I like to split it up two ways, because there's a conventional right-hand rule and then there's another one that I like to use. So the convention is we do it the same way with a current carrying wire. We see that the current is going counterclockwise around this loop. It's going counterclockwise around this loop. If we grab this wire, let's grab this wire right here like we did with a straight wire. going to grab it with my right hand, and my thumb is pointing in the direction of the current. So my thumb is pointing to the right now. If I grab that wire and curl my fingers into the loop, when my fingers pass through that loop, they're actually pointing up. They're pointing up like this. So my fingers will point in the direction of the north pole of this simulated bar magnet, right? So this single loop behaves like a bar magnet. My right hand rule, the way I like to do it, if you like that way, that's fine. I have another way which helps me with coils in particular. I'm going to grab this. Let's say this was a cup, right, or this was a glass, and I was about to take a drink out of it. I'm going to take my right hand, and I'm going to grab that coil. I'm going to grab that loop, but I want to grab it with my right hand so my fingers are curling in the direction of the current. So if you just picture yourself reaching into your computer screen with your right hand and grabbing that wire like it's a cup, your fingers are naturally turning counterclockwise around that loop, and that's the direction of the current, which is good. That tells me my thumb is pointing up right now. My thumb is pointing up right now, so that tells me my thumb tells me the direction of the north pole of the magnet. Okay, so there's two different right hand rules you can use to find the direction of the magnetic field generated by a loop or a coil. So this circuit right here, a coil connected to a voltage source, is generating a magnetic field inside of it, just like this. Okay, just like this loop, this coil right here. So another thing that we notice is, let's say this bar magnet, kind of picture like maybe a horseshoe magnet or something like that. This bar magnet, let's say it's all the way over here. Okay, so it's not even close to this coil. There's not going to be any current generated in this wire. If you bring the magnet close to it, there are magnetic field lines going from north to south. Right, so the B field generated by this magnet is going from north to south. So there are a bunch of field lines. So if I bring it close to the magnet, I'm going to have a magnetic field now inside the coil. And again, momentarily, the current needle is going to deflect. If I leave this magnet here, the current is going to go back to zero. Okay? So the moral of the story is, for all three of these cases, my magnetic field has to be changing. I've got to have a change in magnetic field for that current, because once that magnetic field is constant, the current needle goes back to zero. And a loop or a coil acts like a bar magnet, but the magnetic field lines are much closer together the closer you are to the coil. So right here, the magnetic field is very, very strong, kind of like our expression for the magnetic field of a current carrying wire. The farther away you are from the wire, the weaker the field. So my magnetic field is really, really strong right here, and then the farther away you get from it, it's weak. So if you move this up, right, you move this up, let's say there's another coil right here, you move this up, you're increasing the magnetic field strength inside the coil. Just like in this example, when it was over here far away from the coil, there's no magnetic field. So you're causing an increase in the magnetic field strength that's inside this coil. And so when there's a change in magnetic field, we see this current needle deflect temporarily. So before we get our mathematical formalism underway, we got to talk about a concept we refer to as flux. Now, if we go back to chapter 19, that torque on a current carrying loop, we had that area vector, right? We had that A vector that was like perpendicular to the surface. So what was happening was the loop was in a uniform magnetic field, and as it rotated, you can picture, if that magnetic field was uniform and it was constant throughout the whole diagram, as you rotated that loop, there were more magnetic field lines passing through that loop. Now that didn't necessarily have anything to do with the torque on that loop, but this is just a good example to talk about the concept of flux. So I'm going to skip down one slide because there's a diagram on the next slide that kind of helps us describe this. So instead of a magnetic field, we're going to take a fan, right? We're going to turn the fan on, and there's going to be a wind direction in this direction. Okay. So picture this as your magnetic field. Okay. So it's constant, right? Fan is on high, and it's on a constant speed. So the wind speed is constant. When this loop is parallel to the floor, you see this one right here? When the loop is parallel to the floor, there's no wind passing through that loop. So all the wind is just passing over it, passing under it. There's nothing actually passing through the loop. When you start to tilt it, some of these wind speed vectors are actually going to be passing through the loop. And then the more you tilt it to perpendicular, the more wind speed vectors are passing through that loop. And then you're going to have a maximum amount of wind passing through the loop when it's perpendicular, right? When it's perpendicular to the floor, all right? Or you can think of when the surface area is perpendicular to these wind speed vectors. That's when there's a maximum amount of wind passing through. So you'd think this would be 0 and then this would be 90, but we're actually measuring the tilt angle from here, from when the loop is perpendicular to the floor. All right. So this is theta equals 0, and then this is theta equals 90. Okay. And the reason we measure our angle that way is because flux is a scalar. Flux is a scalar. You can think of it as like an amount of stuff that's passing through, kind of like current. It's an amount of stuff that's passing through this loop. So when the loop was perpendicular, the airflow was at a maximum. When the loop was parallel, the wind passing through the loop was at a minimum. So it's you think about the amount of wind, okay? The amount of wind is proportional to the area that is available for wind to pass through it. So that area was AB, okay? But it's also dependent upon the angle. And so we use cosine theta because it's at a maximum when this theta is 0. So cosine 0 is 1. And it's at a minimum when theta is equal to 90. And we use cosine because it's a scalar product. Flux is a scalar. It doesn't have a direction. So it's going to be at a minimum when theta is equal to 90. Cosine of 90 is 0. All right. So here's another diagram. Similar process here, but now we're talking about an electric field, or excuse me, a magnetic field, right? So instead of our wind, we've got our magnetic field vectors. Okay, we've got the most amount of magnetic field passing through here when theta is equal to 0, when the loop is perpendicular to the magnetic field, and then as we tilt it, right? We tilt it, it's about to be parallel, there's less area, right? There's less surface area of the loop that's perpendicular to the magnetic field. And then finally, when we're parallel, there's no magnetic field passing through. So you see that the magnetic field is actually changing, right? The magnetic field that's present through this loop is decreasing, right? So it's at a maximum here. We've got fewer magnetic field lines passing through, and then finally we've got no magnetic field lines passing through. So it's proportional to the area of the loop, right? It's proportional to the area of the loop, A, B, and then cosine theta. It's dependent upon that tilt angle. So just like we talked about that area vector, right? The area vector is a vector that's perpendicular to the area that loop makes. Remember that torque area vector we used? This is the same thing. All right, so whatever the area is of this loop or this coil, it's got an area vector. It's got an area vector that's perpendicular to it. Okay? its magnitude is the area of the loop, and its direction is perpendicular to the plane. Okay, it's got units of meter squared because it's an area. And so our magnetic flux, we use a capital phi, is actually the dot product between the area vector and the magnetic field strength. So if you've got a stronger magnetic field, you've got a stronger flux. If you've got more area that's open or available to a magnetic field passing through it, you've got a larger A. And again, that's why we're using cosine theta. Flux is a scalar, right? Flux is a scalar component. It's the dot product of A and B. It's dot product A dot B. So we call these units of flux are Webers, and a Weber is a Tesla meter squared. Tesla for magnetic field, meter squared for area. So here's our first formula. Magnetic flux, capital Phi, is the magnetic flux. Think about it as the amount of magnetic field that's passing through a loop. So we've got Faraday's law. Faraday's law is actually a formula for the voltage, right? The voltage that's induced in a coil due to a changing magnetic field. Lenz's law is that there is an induced current in a closed loop due to a changing magnetic field. So Lenz's law and Faraday's law are very closely related. Faraday's law, I'll show you the formula in a later slide. But Faraday's law tells us the induced voltage in a circuit due to a changing magnetic field, and then Lenz's law tells us the induced current in the coil due to a changing magnetic field. Now Lenz's law doesn't have a formula that we're going to use. We're going to use the formula for Faraday's law, and then if we know the resistance of the circuit, the equivalent resistance of the circuit, or the resistance of a piece of wire, right? Resistivity and the dimensions, we can calculate the resistance. We'd use Ohm's law to calculate the induced current. But again, the same thing happens. Faraday's experiment was dealing with this current meter, right? He noticed that there was a deflection in the current needle every time. So Faraday's law and Lenz's law are very closely related. So if we go back to the first experiment, we're going to take this magnet and we're going to drop it into the coil. Okay, we're going to drop it into the coil. Now what we're doing, I'm going to do quite a few examples of this, and we've got a WebAssign problem that deals with this too. So I'm going to drop this magnet in. So what's happening is if you picture the magnetic field lines, they go like this. They kind of go like in a circle like this. They go from north to south. So the magnetic field is pointing in the negative y direction. When you lower the north end of the bar magnet, you are actually increasing the magnetic field strength inside this coil. Remember, the field lines are much closer together when you're closer to that coil. So the magnetic field due to the bar magnet is increasing in this direction. It's increasing in this direction right here. Now what happens is, and for lack of a better term, there's a very sophisticated explanation of this, but to think about it practically, this system was in equilibrium, right? This loop and this current meter, they were all happy. Everything was fine, right? And then this magnet comes around and starts changing a magnetic field inside of it. Well, the circuit wants to go back to equilibrium. This is kind of how I picture it conceptually to get my direction straight. So this changing magnetic field is in the negative y direction. This system doesn't like it. And so there's going to be an induced magnetic field in the opposite direction. Right, so there's a magnetic field that's kind of opposing the change in flux. Right, so this is B induced. B induced is always opposite the direction of your change in magnetic field. Right, so we're bringing the magnet in closer. Right, bring the magnet in closer. the magnetic field is increasing in the negative y direction, so there's an induced magnetic field in the positive y direction. So there's an induced current that's related to the induced magnetic field. How do I determine the direction of the induced current? I got to use another right-hand rule. Use another right-hand rule. And so this right-hand rule, the final right-hand rule, hopefully, thank goodness, I think we're on like right-hand rule number 7 or something. This right-hand rule goes like this. I'm going to point my thumb in the direction of the induced magnetic field. So I have to determine the direction that the magnetic field is changing, point my thumb in the direction of the induced magnetic field with my right hand, and then curl my fingers around the loop. And that tells me the direction of the induced current. So my thumb is in the direction of the induced magnetic field. My induced current is counterclockwise around the loop. And so when you bring this bar magnet in, B induced is out, or it's up, and then the current is counterclockwise, hence the deflection this way, right? Hence the deflection this way, because the induced current is counterclockwise around the loop. So that's how the current meter reads it, right? It deflects in the direction of the conventional current, right? So the current's going around the loop, comes through this wire into the current meter like that. We've got a deflection. So that's Lenz's law. We're going to go through a couple examples where the magnetic field changes direction, right? We'll use our right-hand rule and find the direction of the induced current. So let's go backwards, right? Now the bar magnet has been in the coil for a long time, and we're going to pull it back up in the positive y direction. So what that means is the magnetic field is actually getting weaker, right? It's getting weaker. So when you pull the bar magnet out like that, delta B is actually in the positive y direction. And I've got some notes that kind of help clarify that a little bit, and I'll show you that in a second. So I pull the magnet back out. The magnetic field strength inside the coil went from strong to weak. It went from strong to weak. So the magnetic field inside the coil is actually decreasing, right? So my magnetic field's getting weaker in this direction. To oppose the decrease in the magnetic field, my induced magnetic field is in the negative y direction. Okay. Again, the system was to be in equilibrium. Once the magnet was in there for a while, you know, the system kind of settled down, was like, all right, I'm fine. And then you brought this magnet back out, it didn't like it again, so there was an induced magnetic field to oppose that change in the applied magnetic field. So I'm going to call this B applied in a couple examples, right? So this is an applied magnetic field. It's due to like an external magnet that I'm bringing into the system. And so we see the current needle will go in the opposite direction because B induced is now in the negative y direction. Use my right hand rule again. Take my right hand, point my finger in the direction of the induced current. So my thumb is pointing down, all right? Thumbs down for physics class. B induces in the negative y direction. My fingers are curling around the wire, but now they're curling in the clockwise direction, right? So that's why we get a deflection in the opposite direction of the current meter. So the theme is the most important thing is to identify how the magnetic field is changing inside the coil. And then when we can identify the direction of delta B, we can say B induced is acting in the opposite direction, and then we use our right hand rule, thumb in the direction of B induced. Our fingers are curling around the coil in the direction of I induced. Okay, so before I do this example, I'll go through a couple of my notes. These are basically my notes for the slides, right? So when I first dropped the magnet in, delta B was in the negative y direction. Why was delta B in the negative y direction? Because B final was really weak, or excuse me, B initial was really weak, and then B final was strong. So B final minus B initial still gives me a net magnetic field in the negative y direction. and so B induced was opposite that. Okay. And then when I pulled the north end of the magnet out, B initial was really strong, but B final was really weak. So my magnetic field was decreasing inside the coil, so delta B was pointing outside of the coil. And so B induced was opposite that direction. Okay. So there's my answer to slide 13. Let's talk about it. All right, we've got a bar magnet that's being pushed towards the center of a wire loop, which is true. So is there a clockwise induced current, a counterclockwise induced current, or is there no induced current? So you bring the north pole in, all right? So if I'm bringing the north pole in, the magnetic field is getting stronger in the positive y direction, right? So delta B is in the positive y direction, okay? So the magnetic field is increasing as I bring it up. So delta B is in the positive y. That means B induces in the negative y. So now I'm ready to do my right-hand rule now that I know the direction of B induced. B induces in the negative y direction, thumbs down, and I'm rotating, okay? I'm rotating my fingers around the coil. And I'm rotating, if I'm looking from above, if I'm rotating around the loop, my fingers are going clockwise, okay? So I've got a clockwise current around the loop. B is increasing in the y direction, so delta B is positive y. B induces negative y. Right hand rule, thumb down, fingers are curling clockwise. Okay, so there is a current in this wire and it is decreasing. Okay, so there's a current in this straight wire and it is decreasing. So now I have to figure out how the magnetic field is changing inside this wire, or inside this loop, and then determine the direction of the current that's going through this loop. Is it clockwise? Is it counterclockwise? So the first thing I'm going to do is I'm going to do the right hand rule for a current carrying wire. So I'm going to grab that loop with my right hand. Okay, I grab that loop with my right hand and curl my fingers around. When my fingers are on the right side of this wire, they're pointing into the page. Okay, they're pointing into the page. So here's a diagram, right? Here's the current carrying wire. The magnetic field due to the current carrying wire is going around like this, counterclockwise, as I'm looking down at it. So on this side of the wire, there's a magnetic field inside or into the page. Okay, so I got a bunch of X's in here. Okay? Got a bunch of X's in there. My magnetic field is acting into the page, negative Z direction. So we turn the current down in the wire. What does that mean? My magnetic field is still going into the page here, but it's getting weaker, right? It's getting weaker. So even though it's still pointing into the page, it's getting weaker. So my magnetic field is decreasing, right? It's decreasing. So B initial is really, really strong into the page, right? B final is still into the page, but it's really, really weak. So the magnetic field is getting weaker, so that means it's changing in the positive Z direction. Right? The magnetic field is going into the page, but it's getting weaker. So the change in the magnetic field is out of the page. All right? So I drew these vectors to represent delta B, the direction of delta B. All right? So delta B is coming out of the page. That means the magnetic field induced by the coil is back into the page. All right? Really weird here, right? So I've got a decreasing current. I initially have a really strong B field into the page, but it's decreasing. So it's changing in the positive Z direction out towards me. So that means B induced is opposite the change of magnetic field. So B induces into the page. Now I've got to use the right hand rule again. So I've got to point my thumb in the direction of B induced. Right hand, thumb is in the direction of B induced, so thumb is going into the page. And so when I curl my fingers around this loop, My thumb is going into the page. When I curl my fingers around the loop, they're curling clockwise. So the induced current here is clockwise around the loop. Choice A again. Okay. So again, this is probably the toughest part for Lenz's law and Faraday's law. Determine how the magnetic field is changing inside the loop, and then determine the direction of that change, delta B. Flip it, that's your direction of B induced, and then use the right hand rule to determine the direction of the induced current. Okay. Okay, so I've got 3 loops now. Okay, 3 loops on either side of the current carrying wire. Okay, so it says 3 loops of wire move near a long straight wire carrying a current. What, if any, currents are induced in each loop and in what direction? So it doesn't say that the current is changing through this wire. So there's a constant current. Okay, constant current. If we go back to chapter 19, use your right hand rule for a current carrying wire. Grab that wire, thumb pointing in the direction of the current, excuse me, and my fingers are curling around that wire in the direction of the magnetic field. So that means I do the right hand rule on this side, okay, on this side of the wire, the current is going into the page. Okay, so I have a bunch of X's over here because the magnetic field is going into the page. Over on this side, it's coming out of the page, right? Your fingers wrap around, they go into the page on this side, come back around, they're out of the page on this side. So what's that mean? The current's the same, right? The magnetic field is the same. Why is there any induced current? Is there? I don't know. If you remember, my expression for the magnetic field due to a current carrying wire is inversely proportional to the distance between that location in question and the wire. So that means the farther you get away from that wire, the weaker the field is, right? The weaker the field strength. So let's talk about loop A first. All right. So it's moving up in this direction. All right. It's moving up in this direction. So it's moving in the positive y direction. It's not moving closer or farther away to the wire, right? It's not moving in the x direction. So that means the magnetic field inside this loop is going to stay constant. R isn't changing, I isn't changing. This is just traveling in the positive y direction. So there's no change in flux. The magnetic field is not decreasing. There's no change in flux. So there's no induced current in loop A. There's no induced current in loop A. Let's do B. All right, loop B. The field is coming out of the page, right? So my initial field is coming out of the page, right? So I picture a bunch of dots in here, But loop B is moving farther and farther and farther away from the wire. So what's happening? R is increasing, right? R is increasing, so the magnetic field strength inside this loop is decreasing. So think of it as like B initial and B final, all right? So for loop B, magnetic field initially is really, really strong out towards me, and then it gets weak as I go farther away. So B initial is really strong towards me, B final is really weak towards me. So the magnetic field strength is decreasing, okay? It's decreasing inside this loop. So that means for loop B, B induced is into the page, okay? B induced is into the page, okay? So it's initially out of the page, but it gets farther and farther away, so it's getting weaker. So delta B is into the page. Delta B is into the page because the magnetic field strength is decreasing. Okay, it's still pointing out towards me, but it's decreasing. So delta B is into the page. Flip it around, get the direction of B induced. If delta B is into the page, B induced is out of the page. All right, B induced is out of the page. Right hand rule, point your thumb towards you. loop your fingers around, curl your fingers around the loop, and you're going to be curling them in the counterclockwise direction. So I induced for loop B is counterclockwise. Okay. B is coming out towards you, but B is getting weaker. So delta B is into the page. That means B induced is back out of the page. Right hand rule tells me counterclockwise loop. And so you might think that the opposite is happening for loop C. You'd be right. The magnetic field is still decreasing, but for loop C, the magnetic field is going into the page. Okay, so B initial is into the page, but as you get farther and farther away from the wire, the magnetic field is getting weaker. Okay, so B initial is really strong into the page, B final is still into the page, but it's really weak. So delta B is coming out towards you. Alright, so delta B, the change in magnetic field for loop C, is out towards you. So I've got to find B induced, right? B induced is opposite direction of delta B. Okay, it's going into the page, but it's getting weaker. So delta B is coming out towards you. Alright, and so B induced is back into the page. Alright, B induced is back into the page. Got to use my right hand rule. Point my thumb in the direction of B induced into the page, and my fingers curl in the clockwise direction. So the induced current for loop C is different than this loop. It's opposite, right? Because delta B is the opposite direction, B induced is the opposite direction. So I've got a clockwise loop for loops, or a clockwise current for loop C. Okay, so I'm gonna pause here real quick because you know, that's some pretty heavy stuff there. So let you go through those examples. You can, you know, try and find some of your web assigned problems that are you know, your Lenz's law, finding the direction of the induced current. Go ahead and practice those. I'll get this video uploaded, and we'll finish with Faraday's law, and we'll do more problems like this. Okay. All right. Thanks. Hope everything's going well. Like I said, let me know. You got any issues with the videos or labs, or you know, the concepts in general? Just let me know. Send me an email, and we'll get together and talk about it. All right. Thanks. See ya.